Hello everyone, I am Chaitanya Dua from ENC.
Hi everyone, I'm Devanshi Arora from ENC.
Hi everyone, I'm Manveer Singh from ENC.
Hi everyone, I'm Raghav Khana from ENC.
Hello, I'm Siddhant Saxena from ENC.
Hi everyone, I'm Vansh Ahuja from ENC.
Hello everyone, this is Group 59. This is the video of our Capstone project named Bibot, which is an autonomous food delivery robot. The team comprises of 6 members: Chaitanya Dua, Devanshi Arora, Manveer Singh, Siddhant Saxena, Raghav Khana, and Vansh Ahuja. We have been fortunate enough to work under the guidance of Professor Kulbir Singh and Dr. Hemdutt Joshi. When we were told to choose the idea of our Capstone project, after brainstorming many ideas, we decided to go with an autonomous mobile robot which facilitates 24 hours food delivery in hostels. The motivation behind this idea was the restriction of food delivery agents inside the campus after midnight. So we decided to create a basic prototype of robot which include an array of sensors for perception. The goal of our project was to develop an eco-friendly and a cost-efficient robot.
The robot utilizes a 2D LiDAR and an RGBD camera in order to enhance feature extraction of an environment. The initial steps involve pre-processing of the point cloud data facilitated by ROS framework. Furthermore, the fusion of these point clouds aid in generating a map of an unknown environment using simultaneous localization and mapping algorithm. After map generation, the robot localizes itself inside the map using adaptive Monte Carlo localization. Finally, a global and local planner is implemented to facilitate autonomous point-to-point navigation while avoiding obstacles.
The autonomous mobile robot relies on Kinect and LiDAR sensors to gather information from the surroundings. The accumulated data is then passed on to the main ROS framework, via which the data is processed and thereby sends low-level commands to the Arduino, which then performs low-level computing to give out velocities, which is channeled out to the motor drivers for the movement. A lithium-ion battery powers the bot for optimal performance. This continuous feedback loop enables to execute the controlled and desired movements.
These executables are called ROS nodes, and nodes communicate with each other through ROS topics. ROS is also very easy to integrate with visualization tools like RViz to facilitate our ability to visualize the point cloud data of the environment obtained by our sensors. Also, physics simulators like Gazebo that allow us to run virtual iterations of the execution of our robot in a simulation environment are easy to interface with ROS. The first step in software implementation with the goal of autonomous navigation is mapping. Initially, separate maps are created with individual sensors. First, Hector SLAM uses the point cloud data obtained from the LiDAR to update a two-dimensional grid map representing occupied spaces. This allows it to efficiently build accurate maps over time. Next, RGBD SLAM uses a camera matching visual features to estimate movement while continuously updating a 3D occupancy map. Although this step collects drift, the drift is accounted for by loop closure algorithm. For fusion, RTAB map is used. It aligns two-dimensional LiDAR scans via scan matching for precise shape and range data while extracting visual features from the camera for discrimination. By integrating complementary data, the post-graph optimization seamlessly fuses the sensors. Adaptive Monte Carlo localization localizes the robot using a particle filter posing hypothesis adjusted by motion and observation models, resampling to focus belief. Before parameter tuning, estimated pose variance is unfocused, but after optimization, it converges precisely on the actual location. The final step is to implement point-to-point autonomous navigation, and this is carried out by the move-based algorithm. The move-based algorithm employs a global planner and a local planner to facilitate autonomous navigation. The global planner charts a course from the robot's current pose to its final pose using Dijkstra's algorithm, accounting for static obstacles present in the map. The local planner is put into effect when a dynamic obstacle is encountered. It avoids the obstacle and puts the robot back on the path planned by the global planner.
This custom-built robot features a robust mechanical architecture centered around a rigid steel chassis which houses its drive motors. The main robot body consists of finely crafted wooden panels forming two distinct compartments: electronic bay that contains the Arduino unit, motor driver, and other sensor hardware, while the main compartment provides secure storage space for carrying food items. This robot also features a responsive forward maneuverability enabled by a differential steering mechanism. A high-precision LiDAR module is strategically mounted on the top panel, delivering reliable 360-degree coverage, and a RGBD camera in the front collects supplementary scene visualization through a slit window.
The backbone of this entire operation is a developed ROS package named Bibot, which encompasses additional sub-packages to facilitate the mapping, localization, and navigation. To make the prototype up and running, there are a series of steps. The first step involves turning on the robot, which activates its motors and both its sensors. The next step involves starting up the ROS core system, after which we activate the nose using robot description command, the sensors using bot bring up command, and the motors using ROS serial command, and the joystick using teleop joy command. The next step involves starting the mapping procedure by entering the following commands, which activates the launch file of our mapping sub-package. Using a joystick, we then teleoperate the robot, which in turn produces a map of the environment. After map generation, we launch the Bibot navigation command, which contains packages related to localization and navigation. During this process, the robot automatically localizes itself in the environment, after which we define the goal point of the robot to traverse to. After these initialization steps, the robot is able to perform any number of point-to-point navigations.
Initial point-to-point autonomous navigation trials, depending solely on LiDAR or RGBD cameras, showed undesirable deviations from target waypoints. Fusing positional output from both sensors enabled reliable achievement of all navigation targets in final assessments. In conclusion, this sensor fusion technique approach demonstrated the highest navigational accuracy over single modality solutions.